Welcome to video 04 in nuLUCA Pavilion's Intro to Grasshopper Part 1 tutorial series. In this video, we'll take the first step in making the glass sponge pattern. And that step will be to pull something out from each of the surfaces we're starting with. We'll make a little component that you plug in any surface that you want, and the first step in making the glass sponge pattern on that surface will be to pull out the bottom curve. This might seem unnecessary since we already have the bottom. We used it to make the surface. But our goal for this tutorial is to make a script that takes in a surface. That's all you need is just a surface. And from that surface, it will generate the glass sponge pattern wherever that surface is and on whatever shape that surface takes. The first step in that process will be to deconstruct the surface a little bit. In Grasshopper, it's important to be able to deconstruct things. We do this all the time. It's important to be able to separate out components of more complex geometry into simpler components and design with those components in different ways. Sorry, I know I've used the word component a lot when referring to Grasshopper components, but here I'm talking about components of geometry. So, like, this is a component that holds a circle. This is a component that makes a circle. If we go into top view and zoom way in here, get a curve component. And then let's make this circle into a surface. And so we can also kind of talk about the components of this circle. That's totally separate than these components of the script. So component, just a general term that's referring to a smaller piece. And so this circle surface, it has a perimeter curve, a bounding curve. You can think of the center as being a component of this circular surface. Or you can think of any point that has an x-coordinate and a y-coordinate that satisfy this equation as being a component of this circular surface. Since all of those points will be on this surface, you can think of those as being components of this surface. So you can think of this circular surface as the set of all points that have x and y coordinates that satisfy this equation. So a component, when I'm using it that way, is just a simpler bit of geometry that's part of a larger geometry. Probably didn't need to go into this explanation, but I just heard myself saying component in so many different ways. Anyway, back to using components of geometry, back to deconstructing surfaces, deconstructing geometry and using those pieces. So maybe we want to use just the points at the corners of a cube for something, or just the midpoints of a curve. Maybe we need the endpoints of a curve. And I should say here, and this is a tiny tangent, sorry, yeah, another tiny tangent, but the word curve was a little confusing to me when I first started Grasshopper, so I'll take a moment just to talk about that. But if you want to just jump ahead, you can go to like the 7-minute mark or something like that if you want to jump right into the tutorial. But as far as the word curve goes, just in case you haven't already figured it out faster than I did when I was learning, the word curve in Grasshopper is referring to any one-dimensional object that has two endpoints. And by one-dimensional, I mean that we only need one value to know where on that curve we are. We just need one parameter. So let me go into the top view to explain what I mean. I'm going to get rid of the grid quickly. And I'm just going to type in CI. This is my shortcut for interpolate curve. I'm just going to make a curve here. And double click and type curve to bring in a curve component. Right click on that and go to set one curve. And I'm going to right click on this and say internalize data. So now this is in the Grasshopper canvas only. And I'm going to delete this curve. It's not in Rhino anymore, just in Grasshopper. And so what I mean by one parameter to describe any point on that curve is this is one-dimensional in the sense that you can only move in one direction once you're on this geometry. And you might say, well, you can move in two directions, forward or backward, but that's just the same direction, but with a negative sign. And so let's get a evaluate curve component and plug the curve in there. Then I'm going to right click and go to reparameterize. And so that just set the curve length to 1. It didn't actually change anything about the curve. It just made a new unit scale, sort of, where this curve has a length of 1, just in this component though. And so at the beginning we have 0, and then it's just pretending that at the end we're at length 1, but This is just referring to what point on the curve we are. And so if you want, you can imagine this in percentages. 1 would be 100%, 0.9 would be 90% along the way of the curve, and so on. And so we only need one number to get to every single point on that curve. So I'm going to get a slider between 0.000 and 1. And you can see that we can reach we only need one slider to reach every point on this curve. So if we go back to perspective, let's look at a surface. So a surface is two-dimensional. So let's get an evaluate surface component. And for this, it's asking for UV, whereas this is asking for T. We only need one parameter to reach every point on the curve, but we need two parameters to reach every point on a surface. So I'm going to right-click and say reparameterize again. And let's just grab this curved surface. And I'm going to type in MD slider. And let's see what's coming out of this component here. This is a specifically formatted output. We have a curly bracket, then 0.5, comma, 0.5, comma, and then a Z value here. So this is X, Y, and Z, you can think of it. But what's actually coming out of here are U and V coordinates. We need two inputs to pick a specific point on any surface. So if we put these in, then you can see we can reach every point on this surface with a combination of these two inputs. The third output here, what I referred to as Z, is always 0 because we only need two parameters. Anyway, that's just a little tangent. And so in Grasshopper, a line is a curve, a polyline is a curve, a circle is a curve. A circle just happens to be a curve where the two endpoints are at the same position. And what we're going to do in this video is grab the bottom curves from each of these surfaces. So let's start this video by looking quickly back at the article we've been referencing by Fernandez et al. And we can see that this is the pattern that we're looking for. We have this double X, an alternating double X, and a little more open one, but the important first step is getting these squares. We need to apply a square pattern, a square grid, with equal length and height for each square cell across all of our surfaces. And this is going to be relatively simple for the flat surface and for the circular surface. So I'll do those two first. It's going to be more difficult, and we'll get to why when we're doing this irregular surface here and the rectangle and the referenced polyline. So one good thing about Grasshopper is you can start with basically anything as your geometry input. So here we started just with a point for each surface, and then we had different parameters adjusting how that surface looks, but the input geometry here is just a single point. And since we want to apply the same pattern onto all of these different surfaces, the starting geometry is going to be surface for each. We're just going to make one component that applies the pattern to any surface that we put in. So our input is going to be a surface. So let's grab all of these surfaces. First, I'm going to group this. So I'm going to grab all of these output surface components and pull them down here. So I'll start by getting this one, Alt, and let's hide this. And let's also hide the wire by going to Wire Display Hidden. Pull that over here. Let's do the same thing for the curved surface. Wire Display Hidden, hide this. And the circle. And the triangle, and the referenced curve. Okay, so now we have all of our 5 different surfaces that can be a starting point for our next component, and we'll just do one at a time. Like I said, the circle and the flat surface are going to be the easiest. I'll start with the flat surface. And the first thing I want to do is get this bottom curve. So obviously we already have it up when we made the flat surface, but let's pretend like we need to start with this surface. And so how would we get that bottom curve? The most straightforward way to do this is to get a component called brep edges. So if I just type brep ed and we get brep edges. So before we were talking about how these little more complicated surfaces can be housed in a brep component. They can be, Grasshopper can recognize them as breps, but not as surfaces. So breps are a little bit more general, and so we can, for that reason, we can put a surface into a brep component, into a brep input, and that's no problem because a surface is a more specific kind of brep. So now we have the brep edges, and so if we click on this, we can see that the edges are highlighted in green. And let's do that for the circle also. We can see the circle has 3 edges. It has these 2, and it has this seam in the middle where the surface comes and wraps back around on itself. Whereas the flat surface has 4 edges. It doesn't wrap around itself, and so it has these 2 vertical edges. And these are differentiated by these different outputs. And so we have, if we hover over here, we can see that this says naked edges, naked curves, and this is interior edges. And as the name implies, interior means that it's inside, it's bounded on all sides. And so if we go back over to the circle, this one's going to be an interior edge, and these ones are naked because they're on the outside. So if we look at the flat surface, we can see that these are all outside edges. These are all defining the boundary. And go back to the circle. And this one isn't defining the boundary, it's defining the seam between where the surface starts and ends. And so let's start by getting a list length component. And I'm going to plug these 2 outputs into the list length component. So this is non-manifold. This we won't need to deal with now. This is for messier surfaces, essentially. This would be for edges that are connected to more than 2 surfaces. Like this, for example, this edge in the middle is connected to 4, whereas naked edges have just 1 surface each. Interior edges have 2, and in what's called manifold geometry, no edges have more than 2 surfaces. That's why this is called non-manifold. But we don't need to worry about this now, just the naked edges and interior edges. All of our edges are going to be either naked edges or interior edges for any of these surfaces. And the list length component is going to do exactly what it says. It's going to tell you the list of the length. So let's get a couple of panels. This is saying that there are 2 naked edges for our circle. And if we copy this, we see that there is 1 interior edge on our circle. It's this vertical edge here. And if we plug in the flat surface, we can see there are 4 naked edges and 0 interior edges. And that makes sense because there's no edges in the middle here. How about if we go to our referenced surface and we plug this into the brep? Now, if we just count and don't look at the output yet, we can see that there are 1, 2, 3, 4, 5, 6, 7, 8 naked edges and 1, 2 interior edges. And so that's right, 8 and 2. Let's go to the triangle. This one has 6 naked edges for the top and the bottom, and 1, 2, 3 interior edges. So you might be able to see a pattern here. The first key difference that we can see between these different kinds of surfaces is some of them are open like this, and some wrap back around and connect with themselves. So these 2 here wrap around and connect with themselves, and these 3 do not. And that's going to make a difference when we're applying our pattern, whether or not they wrap back around. And so we need to somehow differentiate between these 2 different kinds of surfaces. And we can do that by paying attention to the ratio between the naked edges and the interior edges. We can see that on the triangular surface, which is one that wraps around, we have 6 naked edges and 3 interior edges. Let's go to the circle surface. We have 2 naked edges and 1 interior edge. Let's look at the flat surface. We have 4 and 0, and the curved, we have 4 and 0, and the referenced, we have 8 and 2. So the key thing to recognize here is that for both of our surfaces that wrap back around, there are twice as many naked edges as there are interior edges. There's exactly twice as many. And so if we do a ratio here between interior edges and naked edges, it's always going to be 0.5. So 1 divided by 2 is 0.5. And for our triangle, we have 3 divided by 6 is 0.5. That's not the case with our open ones. So 0 divided by 4 is 0. It's not 0.5. If we get our referenced one, 2 divided by 8 is 0.25. It's not 0.5. So that's where the difference is. And if you take the time to think about this, it makes sense for the kinds of surfaces we made. And if we're looking at the bottom curve, for a curve that closes back in on itself, there are going to be the same number of seams as there are surface segments. So the same number of surface seams between surfaces as there are surface segments. So I'll introduce the term discontinuity here. It's pretty self-explanatory. Every time the curve makes a sharp change in direction, there's a discontinuity. So there's one at the start of the curve and there's one at the end. And then even if the curve is curvy, if the curve's not continuous, I think technically when the tangency is not continuous, or when the slope of the curve makes a jump, when there's a literal break in the derivative of the curve. Anyway, everywhere there's a discontinuity, there will be a seam or a naked edge. But in the case of surfaces that wrap back in on themselves, there will only be seams whenever there's a discontinuity, and these seams are interior edges. So for the surfaces that wrap back, the number of naked edges is equal to twice the number of seams, since at every discontinuity, a new naked edge starts on both the top and the bottom, so times 2. And those will be the only naked edges because, again, it wraps back in on itself. So naked edges will always be twice interior edges on surfaces that wrap, but on surfaces that don't wrap, the number of naked edges will always be more than twice the number of interior edges because we have these extra 2 start point and end point edges, at least for the kinds of surfaces that we made. So these list length components give us the number of each kind of edge we have, naked and interior. And so we can do a division by typing a slash for division and enter. And we need to put this one on top because sometimes this will be 0. We don't want to divide by 0 and divide the interior edges by the naked edges, and we're going to get a number. So it's 0.25 in the reference case. For the triangle, it's going to be 0.5. For the circle, it's going to be 0.5. And for these, the curved surface and the flat surface, it's going to be 0. And so every time it's 0.5, we need to note that because that means it's a closed, the surface comes back and meets itself. And so in order to make note of that, in order to contain that information in a component, let's first get an equality component. And I'm going to use a panel in a different way here. So double slash, enter, and then actually I'm going to do it this way. So if you want to get a panel with text inside of it, you can just hit double slash and then write whatever you want. So I'm going to write 0.5 because that's the value we're evaluating here. And it'll give me a panel with 0.5 and I can just plug that in. And so what this component is doing is checking to see if the output here, let's grab this and copy it. It's checking to see if A is equal to B. And in this case, 0 is not equal to 0.5. And so the output is false. But if we plugged in the circle, 0.5 is equal to 0.5, so the output is true. And so with this component, we're going to get a Boolean, something to just house this information, to hold this true or false information. We're always going to know if it's true, then it's wrapped. If it's false, then it's not wrapped. And so I'm going to call this wrap. This will be important later. For now, let's just group it and note what this little section of the script is doing. Get wrap Boolean. Again, a Boolean is just a true or false value. And so later when we need to know whether the surface is wrapped or not, we can just grab this component or grab the information inside of this. So that's the first step. Next, if we go back here, remember we need to make these squares. And so we're going to start making these squares by dividing the bottom curve into an equal number of points. And so right now we're on the circle. So the first thing we need to do, since we have all the edges, is find which one is on the bottom. let's just merge these into one component. We actually don't need to consider the interior edges because those will never be at the bottom, but it's probably good practice to have to sort through more kinds of edges to pick the right one. So we have all the edges in here. I'm going to move this down a little bit. And just to make sure that this is a list output, it is actually a list output, and we can check, and it should always be, but just to make sure, I'm going to go to flatten. And flatten will always make this, whatever's coming out, into a list. Don't worry if this doesn't make sense right now. It takes some time to get used to how data is organized here, but it will begin to make a little bit more sense later. For now, if you just go to right-click here and click flatten, then that ensures that all of this coming out of here is a list. So if we're starting with a surface, how do we find which of these three curves is the bottom one? And how do we make a component or a little script that always finds the bottom one no matter what? We can start by seeing where the midpoints of these, in this case, three different curves are. And so we can type in curve middle and plug those three curves in, and you see that it's going to give us a point at the midpoints of all three of these curves. And so if we switch over to the flat surface, you can see now since there are four different curves, we have four different midpoints. Let's go back to the circle for now. And let's deconstruct these points. Type in deconstruct, and the component's just called deconstruct. You can deconstruct a lot of different things. You can see deconstruct vector, deconstruct mesh, but the plain deconstruct component deconstructs a point. And so we have three different points here. We're going to put them all into the deconstruct point component. And what we're interested in here is the z value. Since we're looking for the bottom one, whichever curve has the smallest z value is going to be on the bottom. So the next thing we're going to do is sort these curves according to their z component values. And so let's double click and type in sort, and the sort list component is what we need. And so the K stands for keys. These are the values that the sort is going to sort according to. So if we put the z values into the key, let's get two different panels to see what's going on here. You can see that we started with three different z values, 8, 0, and 4. And after we sorted these key values, now it goes 0, 4, and then 8. And so it's sorted these values in ascending order. And the reason it has another input here, and it can actually have as many as we want, is it can sort multiple lists according to these key values. And that's good because we want to sort these curves according to their z coordinate values for their midpoints. And so we have curve, midpoint, grabbing the z. But let's go back to these curves and let's sort these also. So now what's going to come out of A is a sorted list of the curves in the same order that these values were sorted. And so let's get a list component or a list item component to see how that list has changed. And so a list item lets you plug in a list, and then it lets you tell it which index of this list you want to see. And so I'm going to get a number between 0 and let's just go up to 8 for now. And if I click on this, the green curve is going to be whichever curve is currently in this component. And so we grabbed index 0 from this list. Index 1 is that one, and index 2 is this one on top. And so you can see how these three curves are sorted according to their the z value of their midpoints. Whereas if we were going to plug this list in, index 0 is on top, index 1 is the bottom curve, and index 2 is the middle one. So let's plug in the reference surface as an example. So we have midpoints for all of the different curves, and then we sorted this list of curves according to each of their z values. And when we plug this in, we can see that index 0 and index 1 and index 2, since there are three different bottom curves, all three of these are at the beginning of the list. And if we go past index 2 to index 3, we can see now it's going up. So index 3, 4, 5, and 6 are all of these ones. And then the last ones in the list are the top curves. So I hope that makes sense, but don't worry if it doesn't, you'll get the hang of it. So let's move on. And like I mentioned earlier, okay, we don't need these for now. You can sort as many things as you want, as many different inputs as you want. And that's also good in our case because we also want to sort the midpoints in the same way. And the reason we want to do that is let's get another deconstruct component. And B is our midpoints, and we're sorting the B midpoints based on their Z coordinate values. And so the first ones are going to be the ones that are closer to the bottom are going to be on the bottom, or are going to be at the top of the list. And let's get a list item component, and let's see what's coming out here. 0 is. I haven't plugged anything in to the index, and so the default here is 0. It's just automatically going to pull out the first item in this list. And so the first item is 0, and that makes sense because the smallest Z value for all of our midpoints is 0. And as you can see here, we actually have 3 different curves and 3 different midpoints that we need if we're going to grab this entire bottom curve. So when we made this, we made a polyline that was technically just one line, one polyline, but here it's been divided into 3 different segments. And that was done when we grabbed the BREP edges. We divided up all these polylines into their edge segments. But now we need to put these 3 back together. And so we need to grab every edge that has an equivalent Z coordinate as our first one here, which is in this case, it's 0. If we started not on 0, if we started like at the Z coordinate 10 or something like that, then we would need to grab, we can imagine all of these a little bit higher, and we would need to grab 10 for each of the bottom ones. But in this case, the lowest Z value is 0. So we need to grab every curve that has a midpoint with a Z coordinate of 0. And so to do that, we know that this is 0 because this is the first value in our Z coordinate list, and we've sorted that list in ascending order. So let's get an equality component, and let's see where these midpoints, since we plugged the midpoints into B, the sorted list of midpoints is here, where their Z values equal 0. And so coming out of this component is going to be a true-false pattern, a Boolean pattern, and I'll show you what that looks like. So it says true, 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 and then the rest are false. And so that means that the first 3 inputs here have a Z coordinate value of 0, and the rest do not. And that's good because these first three midpoints, which were sorted here, are associated with these first 3 lines that we plugged into A. So again, if we get out our list item component and we take a look at our lines, which are in A, let's go 0 to 9. So here's our lines that are sorted now. We can see that line 0, line 1, which is over here, and line 2, these are our 3 bottom lines. But if we go to line 3, we can see that that's not a bottom line anymore. But we only need these first 3, so 0, 1, and 2. And so this pattern is telling us which of these lines we need. And so the next component that we need is called call pattern. So type in call and pattern should pop up, call pattern. And this is the pattern. This is a true-false pattern, and that's what this input takes in, pattern. This is a Boolean pattern that it's looking for, and so let's put that pattern into the pattern input. And which list do we want? We want this sorted list here. And so now it's taken out everything that said false and only kept the true values. And so we can see that we have these 3. These are our bottom 3 curves. We don't need this anymore. And we can hide all of these. And so let's plug in some other surfaces to make sure that this works for any of them. Let's plug in the triangular surface. and we can see that it grabbed the 3 bottom ones. For the circle one, it grabbed just this one circle curve on the bottom curve. It grabbed this bottom one. And for the flat surface, yep, we see that the bottom one is green. Okay. Now we need to remake this into a polyline, or to join all of the curves that are in this component right now. Right now this is just a list of curves, and we want it to be just one curve. So just one polyline, and that's easy to do. You type in join curves, put that in, and the output here is one polyline curve. Okay, now that we have our bottom curves, the next step is to divide those curves into straight segments of equal length, and we'll start that in the next video.